Hello, I'm Bill Faulkner, and welcome to the 2018 SMRT Safety Video Podcast. This series of videos is produced exclusively for the SMRT. In this third video of the series, we're going to take a look at RF coils and specifically how they factor into MR safety. So let's get started. As a bit of a review, remember that radio frequency coils are configured to function in one of three modes. They can be designed to only transmit RF or to function as a receive-only coil. Coils can also be designed to function as both a transmit coil and a receive coil. With regards to safety considerations, only coils that can transmit will be of concern in most clinical situations. Receiver and transmit coils can either be designed as being linearly polarized or circularly polarized. The earliest transmit and receive coils were linearly polarized, and in the transmit mode, linearly polarized coils are inefficient in that basically half of their power is essentially wasted. As such, generally, linear polarized transmit coils would result in higher SAR levels as opposed to circularly polarized coils of the same size. Linearly polarized receiver coils are actually not capable of extracting the full information from the MR signal, and as such, the resultant SNR is a square root of 2 less than a circularly polarized coil of the same size. All modern human MR systems today utilize circularly polarized transmit coils. Here are two examples of transmit and receive coils. On the left is a transmit and receive head coil, and on the right is a transmit and receive extremity or knee coil. Notice that the overall appearance of the coil is somewhat similar, but remember that you can't really tell what type of coil it is simply by its appearance. So from an MR safety standpoint, it is very important to make sure that your coils are clearly labeled. As we'll see here shortly, some implants or devices have conditions of use that require a specific type of coil, for example, a transmit and receive head coil. Here are a couple of examples of receive-only head coil on the left, and on the right's a head coil, but this one also has the capability of imaging down in the neck. This is a photo of a whole-body superconducting 1.5 Tesla MR system with the covers removed. And here you see a photo of the integrated RF body coil. This body coil is used to transmit when a receive-only coil is utilized for detection of the signal. It's worth noting that receive-only coils are currently the most commonly used type of coil, local coil, today in modern superconducting cylindrical bore magnets. Here's some clinical examples of conditions of use that mention the specific type of coil that should be used. The top example is from the MR conditions of use for a DBS, or deep brain stimulation system, and it states that one cannot utilize a receive-only head coil since the integrated body coil will be transmitting. Additionally, they cannot use a head transmit coil that would extend over the chest. Now, keep in mind that currently head coils that would extend over the chest are typically receive-only coils, but they are contraindicated based on that previous statement that you can't transmit with the integrated body coil. The second example also mentions not using a local transmit coil on the chest, trunk, or shoulder regions. Now, statements like this are sometimes confusing because the types of coils that are mentioned here do not exist in product form. Nevertheless, it's important that all technologists and radiographers know what types of coils are available and utilized on their MR systems. As an aside, it's worth mentioning from a safety standpoint that when you're using a receive-only coil, during transmission, when the body coil is energized, the receiver coil is detuned from the resonant frequency. This is so as not to induce significant currents within the coil. When the transmission is over, then the receiver coil is retuned back to resonance and the signal is sampled. This is why it's important that when you're scanning with a receive-only coil, this coil should always be connected. Never scan with a receive-only coil that's not connected to the MR system, because then the software will not know that the coil is present and the coil will not be detuned during transmission. This can result in massive current within the coil. The least thing that could happen and is likely to happen is the coil would be damaged or destroyed. Worst thing that could happen is it's damaged and destroyed, and it also could burn the patient. Since transmit coils, or at least knowing which transmit coil you're using, are the coils that are most important to MR safety conditions, let's next look at the differences between linear and quadrature transmit coils. And by the way, another name for a quadrature coil is circularly polarized, or simply CP. Let's start with a look at how a linear transmit coil produces the B1 field. In this illustration, the B1 field is depicted by the green arrow. It's oscillating at the same resonant frequency, omega sub 0, as the spins. The B1 field can be decomposed into two counter-rotating subfields, in this case represented by the red and blue arrows. Each is half as large. Now, one of these subfields will rotate in the same direction and frequency as the spins undergoing NMR. The other subfield is going to rotate in the opposite direction and frequency. Now, only the positive rotating subfield is effective at inducing net nuclear transitions from the low energy state to the high energy state, and therefore tipping the tissue's net magnetization into the transverse plane for sampling. The other subfield, the negative rotating subfield, is ineffective for MR imaging and serves only to drive the E field and results in unwanted thermal energy being deposited into the tissue. The earliest types of RF coils for MR imaging were all linearly polarized, and in this configuration, both transmission and reception of electromagnetic radiation took place along a single axis. In the transmit mode, linearly polarized coils are inefficient in that half their power is wasted, as previously mentioned. In the receiver mode, again, they're not capable of extracting the full information from the MR signal. Quadrature transmit is much more efficient. In a quadrature transmit, two circularly polarized coil elements, or channels, produce electromagnetic field vectors that are 90 degrees with each other. This results in the circularly polarized transmit coils producing a rotating B1 field, as you see illustrated in this animation. A rotating B1 field is more homogeneous and it has lower RF power deposition compared to linear transmit coils. A common design of circularly polarized or quadrature transmit coils is often referred to as a birdcage design, and here you see two examples. A technology recently introduced primarily for 3T MR systems is referred to as parallel or multi-transmit. Now, a standard circularly polarized transmit coil or quadrature coil will be driven by one RF amplifier. A multi-transmit coil will be driven by two or more RF amplifiers. Here's a diagram of an RF body coil driven by two RF amplifiers, and again, this would be referred to as a multi-transmit, and in particular, this particular configuration would be referred to as a two-channel transmit system. Here's why this is useful. Now, as I said before, the technology is primarily being utilized at field strengths of 3 Tesla or higher, and there are several benefits, one being a significant reduction in dielectric shading. And this is what you see illustrated here. On the left image, this was acquired using conventional circularly polarized transmit coil, and the dielectric shading is obvious in the anterior part of the liver. The image on the right was acquired using a two-channel transmit coil. As you can see, the use of multi-coil transmit results in a reduction of dielectric shading, primarily due to the production of a more uniform B1 field. The reason why it is important to understand that B1 transmit using multi-transmit coil technology is different than when transmitting with standard circularly polarized coils is that some implants and devices may have a condition of use stating that RF transmit should be done only using a quadrature transmit body coil or quadrature mode, not multi-transmit. And this is most likely because the way the device was tested was using a quadrature mode, not multi-transmit. If this is the case, then should you be imaging one of these implants or devices, then you would be required to switch to a quadrature or CP transmit mode. Here's an example from the 3T conditions of use for a conditional pacemaker. Note that it states 3T whole body transmit RF coil excitations. It says 3T MRI systems using 2 transmit channels or fewer may operate in the following RF excitations: 2 transmit channels known as multi-channel 2 or circularly polarized system. Systems that use more than 2 transmit channels have not been studied, but such systems should be operated in the circularly polarized or multi-channel 2 mode if available. So there again may be other devices that state you can't use multi-channel or multi-transmit. When you see a condition of use that states quadrature transmit only, it's referring to the standard way one would transmit prior to the introduction of this multi-channel or multi-transmit mode. So again, you need to know if your system, number one, has this capability, and number two, if it does, when necessary, how do I switch between multi-transmit mode and circularly polarized or quadrature transmit mode. And that brings us to the end of this particular video in our series. Be sure you keep an eye out for the next one. I want to thank you for watching. I hope you found the information useful. So until next time, this is Bill Faulkner. Thanks again, and take care.